car batteries may die, but that doesn't mean it's the end of the road for their components. These lead-acid batteries are routinely recycled. This keeps toxic materials out of landfills and gives those old car batteries a lot more mileage. This battery may be toast, but it's not trash, because dead car batteries are jump-starting a major recycling industry. Pallets of old batteries are tipped onto a conveyor belt. It takes them up into an enclosed machine that has over 30 rotating hammers. They smash the old batteries to bits, and then a screen filters out the lead-acid paste. The broken bits of lead and plastic tumble into a vat of water. The lead and other metals sink, while the lighter plastic pieces float to the surface. A convenient way to sort and separate the battery components. Once the plastic pieces have been cleaned, a machine blows them into the back of a truck. They'll be taken to a plastic recycling plant and turned into pellets that will eventually be used in the production of new car batteries. A worm screw now moves the lead and other metals to another part of the plant for further processing. Remember that lead-acid paste screened out of the smashed-up batteries earlier? The acid has been neutralized and turned into water. This press squeezes the water out, so all that remains is a lead paste. It's removed and added to the pile of lead and other metals. The water from the deacidification process contains some metallic residues, so it's treated with chemicals that cause the contaminants to precipitate, then settle into a sludge on the bottom of the tanks. Workers sample the water to make sure the particles are settling properly. They pump out the sludge, then filter the water, which now meets regulatory standards and can be poured down the drain. The sludge goes into that big pile of lead and other metals. A few shovels full of refined coal are added to the pile as a processing aid. Then the battery solids head up a conveyor into a revolving dryer. The metals spend 20 minutes in here to remove any excess moisture. Then, it's into a furnace for 10 hours. The lead melts into a liquid and the other metals float to the surface, allowing them to be skimmed off. The molten lead goes into a steel kettle where it's mixed with caustic soda. This causes some remaining contaminants to float to the surface for easy removal. The liquid lead is now fairly pure, so it's time to pour. The lead is pumped into bar-shaped molds, and any lingering impurities are skimmed off. Below, a constant spray of ice-cold water chills the molds, and the lead hardens into bars in just 4 minutes. The conveyor winds downward and the bars are tapped free of their molds. There's enough lead in one of these bars to make 3 car batteries. They'll be remelted and molded into battery components. And the final product is as good as new, proving that recycling can give old car batteries new life while keeping dangerous substances out of our landfills. Before refrigeration, people stored foods in underground cellars or shacks filled with snow and ice. Then in the early 1900s, a French inventor developed the first machine to cool and preserve foods at home. The modern refrigerator comes in countless styles, sizes, and colors. Manufacturing begins with coiled sheets of steel. Just one of these coils produces hundreds of fridge exteriors. The interiors are made from rust-resistant aluminum, lined with an acrylic shell. A shearing machine slices the steel into pieces for the exterior top, back, and sides. Then, each one goes into a computerized punch press that makes the holes for running various wires. A brake press forces the steel against a forming die to create edges. Next, workers place the pieces of the refrigerator's outer shell in an assembly jig which holds them firmly together. Now for the fridge's interior. A vacuum forming machine heats a sheet of plastic and shapes it against an aluminum mold. Then, a router carves off all the excess plastic. The freezer half of the refrigerator slides perfectly into the metal outer shell, and the fridge side follows. Copper tubes filled with heated gas are laid along the outer edge where the door contacts the fridge. The gas prevents moisture buildup. A pre-cut face frame goes onto the assembly. Then, foam is injected into the cavity between the interior and exterior shells. This foam not only insulates the refrigerator, but gives it structural rigidity as well. This evaporator plays a key role in keeping things cool. It draws the heat out of the freezer and its contents. Next, the electrical control panel goes into place. It connects to a maze of wires and eventually a microprocessor. With the freezer side almost complete, the fridge side gets its evaporator. Next comes the refrigerator doors. Two compressors pump fluid and gas through the various tubes inside. This component, called the radiator, dissipates the heat collected from the food. Workers attach the expansion valves. These allow the pressurized liquid coolant to expand into a cold gas that circulates through the refrigerator's tubes. Copper tubes are soldered to the compressor. Later, they'll be filled with refrigerant. Temporary quick connect valves allow the system to be charged with inert gas to check for any leaks. The fill hoses are connected and the gas flows in. Inspectors use this wand to check the tubes for escaping gas. If there's a leak, the gauge spikes out of the specified range. Refrigeration occurs as cold gas in the evaporator coils pulls heat energy from inside the fridge. The compressor then changes the gas back to a liquid, while the radiator dissipates the collected heat. The expansion valve turns the liquid back into a cold gas, and the cycle repeats. With a charging gun, workers inject refrigerant gas into each tube, then weld the ends of the tubes shut. Now for the finishing touches, starting with the refrigerator handles. Drawers for fruits and vegetables slide right in. So do the rest of the pre-made shelves and compartments. Finally, an adhesive logo goes onto the door. Built-in, standalone, double door, or traditional, the refrigerator keeps our food fresh and cool just the way we like it.
The ballpoint pen was designed as the answer to the fountain pen's many annoyances. The hassle of having to manually refill the barrel with ink that dried slowly and often smudged. The ballpoint has a tiny steel ball in its tip that applies quick-drying ink from a ready-made cartridge. When the ink cartridge inside these retractable pens runs out, you simply replace it with a new one. Working from the initial design, the pen factory makes molds for all the pen's plastic components. The injection molder first shoots hot liquid plastic into molds for the barrel's rigid core, then into other molds for its soft rubber grip. The tubes for the ink cartridges are also made of plastic. Machinery aligns them in the same direction, then prints on the company name, model number, and tip size. Here, a filling machine injects 0.8 grams of ink through the tip. To prevent the ink from evaporating, it plugs the other end with 0.1 grams of silicone paste. Meanwhile, high-precision machines progressively shape the pen's tip out of stainless steel blanks. The equipment drills a 1 millimeter channel through the blank. Then, in quick succession, fashions the tip into a cone, cuts 5 tiny ink flow channels in the ball socket, and seats a 1 millimeter diameter stainless steel ball in the center. Another machine that inserts a finished tip in each ink-filled tube. A scanner then checks the length and the ball of each cartridge. This magnification shows the width of the 5 ink flow channels next to a human hair. Random samples undergo an air pressure test to check the ball's position and movement. Anything less than perfect will clog the pen. They close off the end of the cartridge with a plastic cap. The cartridges now go into a centrifuge, which forces the ink to the tip, eliminating any air bubbles that would obstruct ink flow. Every cartridge passes through this writing test machine. That blue light is a sensor that triggers the machine to reject any defective cartridge. The components now come together in the assembly department. The machine assembles the clip, sleeve, and barrel. The clip is made of chrome-plated spring steel, a strong metal that regains its shape when flexed. The machine then flips the assembly over to receive the internal components. First, the pen's 2-part push-button mechanism. Part 1, the plastic push button. Part 2, a device called a rotor. With each click, it rotates the refill 45 degrees, so the tip wears evenly. The ink cartridge goes in tip side up, the plug on the back fitting into the rotor. This device forces spring steel wire through a coiling block. This produces a tiny spring that provides resistance to the push-button mechanism. A grabber places the spring over the cartridge tip. Now they close up the pen by adjoining the barrel's bottom part. The machine screws the 2 parts together to a specific tightness. The final assembly machine tests the push-button mechanism to ensure it retracts the tip properly. This also prepares the pens for packaging, as they go into the boxes with tips retracted. The factory subjects random samples to endurance testing. This device clicks the push button 100,000 times. Only then does a printer put the logo on the barrel. This company's engineering of its ink flow channels and tip delivers on average 2.5 miles of writing per cartridge. When roller skates were invented by the Dutch in the 18th century, they put a whole new spin on skating. Before that, people could only skate on iced surfaces, so the sport had definite seasonal limitations. The wheels of those first roller skates were wooden spools, but today's manufacturers have come up with some better tricks to make them. Roller skates have improved by leaps and bounds. The wheels are made of strong, lightweight polyurethane, so there's nothing to hold you back. They start with the shoes. A die press punches out leather patterns, called quarters, 4 per shoe. They place 1 quarter under a foil strip, and a hot die stamps it with the manufacturer's trademark. Then, using a template, they mark the locations where components are to be sewn, such as these racing stripes. They stitch them onto the leather quarters in 2 rows. The 4 leather quarters have been partially pieced together. Here, the operator finishes the job, sewing the shoe's outer layer to the liner. She then stitches the rest of the liner to the shoe, while a little blade on the machine trims the excess leather. Now the roller skate shoe really takes shape, as she folds the leather in 2 and sews the toe. This machine punches holes and inserts eyelets for the shoelaces. This machine, called a laster, glues the shoe to an insole. They insert a shoe and insole together into the laster. Its nozzles coat the toe of the insole with cement, while pinchers pull the leather around it. Then, automated arms press the leather onto the insole, bonding them together. Another machine then nails the rest of the shoe around the insole, and a worker pounds them in further. A final laster folds the edge of the shoe around the heel and then drives nails into it. The hot lights of this machine activate cement that's been applied to an outsole and the shoe body. This allows the two to adhere. As the cement dries, this hydraulic machine presses the outsole to the shoe to aid the adhesion. They stitch the outsole to the shoe for reinforcement. After all, roller skate shoes have to hold up to the rigors of the sport. They insert nails into holes of this heel attaching machine. Then position a fiberboard and leather heel on it, followed by the roller skate shoe. Mechanical drivers thrust the nails up into the shoe, firmly attaching the heel. An operator then forces the rubber sole against a circular cutter to remove the excess material. Next, they screw a polyurethane toe stop into a skate frame. They drill through holes in the frame to make corresponding holes in the shoe. They push bolts into the holes. Then, using a pneumatic socket wrench, they bolt the skate frame to the shoe. The bolts are too long, so they cut them down to size with a special break-off tool. They slide polyurethane cushions onto kingpins, then install bearings in the hub of each wheel. A carousel conveyor delivers the wheel and bearings to a tool that presses them together. With the wheels now linked by axles, these skates are almost ready to roll. They mount each wheel assembly on a kingpin, then install a second cushion ring. These cushions can be adjusted by the skater to change the feel of the skate. A tweak to the axle confirms the wheels spin freely. It takes about 4 days for the experts to make a pair of roller skates. That's somewhat less time than it takes for the average person to master using them. Years ago, making rope was a time-consuming process. They stretched yarn 700 to 1,000 feet, sometimes down alleys, and secured it on hooks. Then they turned wheels to rotate the hooks, twisting the yarn into rope. This technique was called a rope walk. Luckily today, we have machines to do all the work for us. These ropes are made from thousands of nylon fibers that are finer than human hair but stronger. To make rope, yarns wind around aluminum cylinders pulled by a turning spool down the line. Then, 3 at a time, the yarns roll over another spool that applies a protective coating of urethane. They funnel through a distribution plate that holds them evenly apart. This ensures they're at an even tension as a rocking spool twists them into one larger yarn. This machine is called the Whirlwind. It twists the yarn and then winds it onto a take-up spool inside. A little arm moves back and forth, guiding the yarn so it winds evenly onto the spool. This is core yarn, and it will be used to make other rope. Now, dozens of spools of nylon fiber unwind at the same time to make jackets to protect the core yarns. The fibers travel several feet over a network of rollers that act as guides and control tension on each individual fiber. They pass through distribution plates as turning bobbins below twist the fibers into yarn. A platform moves up and down to evenly wind the yarn onto the bobbin. They place 48 of these bobbins on the maypole machine, so called because the braiding action resembles a dance around a traditional maypole. The bobbins spin and zigzag around each other as the machine pulls core yarn up through the center. Here you can see the rope being braided around the core yarn as it's pulled up through a die. This is the braiding action in slow motion. It produces a mountain climbing rope, strong yet stretchy because of the twist in the core of the rope. The rope winds onto the wheel as it pulls it upwards, then it spills into a basket. A worker pulls out a sample rope to check its flexibility and strength. He bends it to make sure it will knot easily. Now, another maypole braider weaves a synthetic rope that's stronger than steel, yet lightweight and flexible. That's because the strands at the core are braided with a material called ultra-high molecular weight polyethylene. It's a high-performance thermoplastic. This rope will be used for advanced yachting. A pulley draws this high-tech rope through some metal pipes filled with steam. This shrinks the polyester jacket around the powerful core for a tight fit. These dancing bobbins do some fancy moves to produce different weaves around core ropes. They dip around in between each other in a choreographed sequence. But there are no worries about production hitting a snarl. If a yarn breaks, the machine simply shuts down. It takes 8 to 10 hours to make around 3,000 feet of this large utility rope. Now for the strength test. They loop a sample piece of rope around steel posts. This one is a nylon double braid, the type used for dock lines on boats. Hydraulic pressure pulls the rope upwards, while a computerized gauge measures the tension and detects the breaking point. Almost 20,000 pounds. That's the weight of a killer whale. Needless to say, this rope is just fine. Now for another test. They insert a steel probe known as a FID into some industrial rope, then place the pointed end into a hole. An electric motor forces the FID through, while a gauge measures the force it takes for it to completely penetrate the rope. It took 10 pounds of pressure to push the probe through the rope, which means this rope is firm yet flexible. And that's how this useful item is made.